Okay, I think we can get started. Good morning, everyone, and good afternoon, depending on where you're joining us from the world. My name is Nirup Sugnaraj. I'll be filling in for Dr. Ranganathan and moderating this today's webinar. So today's webinar is titled Detection of Anomalous Data and Malicious Sensors in Connected and Autonomous Vehicle Networks. And our featured speaker today is Dr. Sanjay Madria. Dr. Madria is a Curators Distinguished Professor in the Department of Computer Science at the Missouri University of Science and Technology. This was formerly called University of Missouri-Rolla. He has published over 300 journal and conference papers in the areas of mobile and sensor computing, big data and cloud computing, data analytics, and cybersecurity. He has won five IEEE Best Paper Awards in conferences such as IEEE MDM and IEEE SRDS. He's also a co-author of a book published with two of his PhD graduates on Secure Sensor Cloud, published by Morgan and Claypool in December 2018. He has also graduated 21 PhDs with two women and two African American students and 34 MS thesis students with 10 current PhDs. NSF, NIST, ARL, ARO, AFRL, DOE, Boeing, CDC-NIOSH, ORNL, Honeywell, and others have funded his research projects of over 25 million US dollars. He has been awarded JSPS, which is the Japanese Society for Promotion of Science, Invitational Visiting Scientist Fellowship, and ASEE, American Society of Engineering Education Fellowship. And in 2012, also in 2019, he was awarded NRC Fellowship by National Academies US. He is a ACM Distinguished Scientist and served as an ACM and IEEE Distinguished Speaker. He is also an IEEE Senior Member as well as IEEE Golden Core Awardee. Dr. Madria, thank you for taking the time today for delivering this talk, and we look forward to the insights that you have. Yeah, you should be able to share your screen.
Okay, thank you, Nirup, for the nice introduction. And I have to share it again. Can you see now?
Perfect, perfect. All yours.
Okay, thank you. So the title of my talk, as you can see, is Detection of Anomalous Data and Malicious Sensors in Connected and Autonomous Vehicle Networks. And this paper basically has appeared in IEEE Mass 2024. So when we talk about, for example, smart city, there are multiple dimensions, in smart cities. One is like waste management, another is smart transportation and disaster management. And I work in two areas with respect to smart cities. One is smart transportation, and that's why the talk is. And I also work in disaster management. So when we talk about smart cities, it looks like this, right? And of course, transportation problem is there in big cities. And of course, this talk relates with cybersecurity issues in the transportation. So what are the challenges of connected and autonomous transportation systems? Of course, we have, for example, several autonomous cars these days, and there are constant firmware and software updates, right? Now, if you do not update, for example, the softwares, and that basically can be because of lack of infrastructure or awareness. So that's an issue, and that basically means you may not have the current security patch, and the malicious people can launch attacks using that vulnerability. And as I just mentioned, like there are, sleeper agents, which basically have these infected vehicles with malware and false information, and then they can basically take control of your car. Also, when we are talking about, the smart transportation, the RSUs plays a important role, which are like these roadside units. And if you do not have sufficient, roadside units, then they may not be able to, for example, even dispatch this current information about the status of the for example, the congestion and other things about the issues like security issues or even some kind of software updates and so on. So, one very popular software which people use in autonomous cars is like AutoSAR, and that AutoSAR also has several vulnerabilities. So, some examples of attacks is one is this Jeep Cherokee, where the vehicle's control was taken over remotely without the driver's consent. And another one is like a Central Texas man hacked and changed a highway sign to say they drive crazy, you all. So the challenges, as I just mentioned, in the connected and autonomous transportation system are there, and there are several uncertainties which basically make it much more difficult. And uncertainties basically originate from two primary sources. One is that partial or no observability of the traffic state. And as I mentioned, like RSUs, for example, they can basically monitor, right, the traffic status. And that can result in a higher degree of variation, of course, at different time of day, if there are some special events. Is it rural versus urban or residential versus central business district? And the distribution of traffic is spatial-temporal, for example. Also, dynamically varying market share of connected assets. So in some region, you have like more autonomous vehicles than others. So the cybersecurity challenges, of course, there are several. For example, the malicious vehicle can inject false or fabricated information within the network, can sniff into the data packets in transit, can perform collision or civil attacks or masquerading attack. They can also basically, uh, play with the, ECUs, those electronic control units. So in general, the attacks can basically happen in many different application domain. So as you can see, even like in underground mine, you have autonomous vehicles. Of course, we have in the transportation. So these networks are there and they're all wireless connections. So for a malicious entity, it's very easy to basically get, you know, into the system and launch attack. So what is the objective for this particular work? Of course, is to avoid accidents in autonomous vehicle due to sensor failure or cyber attack. Also to detect these potential anomalies from sensor data in autonomous vehicles. Remember that, autonomous vehicles have tons of sensors, right, doing different things. Detection of malicious sensors to help formulate preventive measures, and also increasing the anomaly detection accuracy because there could be multiple anomalies in particular sensors. And of course, more importantly, detecting these anomalies, for example, by capturing only a single sensor values. So I'm not talking about like correlation among the values, and then to try to detect anomalies. There are a lot of work, but here I'm only talking about detecting the anomalies from a single sensor values. So what are the challenges? Of course, identify the specific sensor being attacked. So not only trying to detect the anomalies, but also trying to detect that particular sensor which may be sending these anomalous data. So detect multiple anomalies in a specific sensors with higher accuracy and multiple anomalies, which I'm going to talk next. And of course, the challenge is also when you do experiments, you are looking for some real data sets. So anomalous data is very rare. So the threat model, as you know, in cybersecurity research, this is very important that I'm trying to develop solution against some threats, right? So the first one is an instant attack. That basically means an attack which basically, change the values between two consecutive sensors. Okay, that's like instant attack. A constant attack is an observation of temporally constant for a time interval and that deviates from typical sensor reading and is independent to the underlying physical phenomena. So this is like it is just sending some constant values irrespective of what sensor is trying to sense. The third one is a gradual drift attack. This is like you have a small and gradual drift in observed data during a time period, right? So it can basically send you the data which is like -1 every 1 second, right? Then bias attack is like a temporary constant offset from a sensor reading. So you may have a base value and then it always try to send some value which is different from that constant offset. So here you can see the threat model. And for example, I was just talking about instant attack, constant attack, gradual drift, and bias. And you can see here, this here is your autonomous vehicle, which has these sensors like accelerometer, speedometer, and GPS. So in this particular work, I'm considering three different sensors where a malicious entity is launching attack. One is the accelerometer. Oops, the second is the speedometer, and third is the GPS values. And then, of course, you can see that physical attacks are launched, and some of these anomalies could be there because of those attacks. And idea is that how we can detect these anomalies. So here is the network model that you have a cloud network, you have these roadside units, and these roadside units basically communicate with the vehicles. So there are intra-vehicle communication, which is basically between the sensors in the same vehicle. And there could be inter-vehicle communication, which is the communication involving the sensor from multiple vehicles. So here is the CAV-80 framework, which we have designed for this work. So let me explain that here. So first, what we have is we have this mixed anomaly test data, which includes the anomalies from multiple sensors like sensor 1, sensor 2, sensor 3, sensor 4, and so on. And then we have a single anomaly training data, and that can come from these different sensors. So this is like multiple anomaly data, this is single sensor anomaly data. Then we have something which is very important for our work, which we have introduced, is the amplification block. So what the amplification block basically does, it try to increase the value of the readings, because if the values basically are, they differ in a very, very small differences are there, then machine learning basically cannot detect. So the first phase is the amplification phase, where we increase the value of anomalous readings so that basically we can enhance the sensitivity of detecting the anomalies. And the amplitude is basically changed both in the training data as well as the testing data. And we basically train this model with this amplitude value, the amplitude amplification values, and that basically make the machine learning model much more robust. Okay? So the second phase is, which you see here, is the optimized omniscale CNN model, and that basically explore every kernel size across the entire length of the time series data, and then try to select, for example, different combination of receptive field size dynamically. And also it will enhance the range of the feature extraction because we are considering many different kernel sizes. Then you see the phase 3 here, which helps in detecting the malicious sensors. So this did help in detecting the malicious value. So you see that once we trained the model with the Omniscale CNN model, you have the classification, which is like anomalous or not anomalous, right? So that's your class level prediction. And then if you see on the top block, I am basically using now also the Omniscale CNN, and that basically gives the feed to the Kalman filter. And that helps me in detecting the attacked sensor. And that's why you see here, then we try to find the accuracy of a score and the name of the attack sensor. So the name of the attack sensor is coming from phase 3. The phase 2 gives me whether the value is anomalous or not anomalous. And of course, as you can see, like for instant anomaly in the amplification, what we do is if the difference between the threshold alpha, of course, how you define alpha is based on your application and the values you are receiving. And for constant anomaly, if the difference is zero, then it amplifies the current reading by a factor of beta. And that beta is basically added into the current readings. So this is the important part in our work, which is you see here the amplification block. So the challenges in the time series classification, of course, there could be different source and record settings are different. So what should be the size of receptive field? What would work best, for example, and how many different receptive fields should be used? So for example, this paper talks about, this omniscale CNNs and our work basically also compare with their work. So here is the optimized omniscale CNN model. So you can see on the top, let's say I have this time series data input. And what I do is I take half of the length of, for example, of my time series data. So on the right hand side, you see if let's say my time series length is L is 10, then I take on the right hand side 5. So you see I have 5 columns and 5, for example, rows. And then I try to basically explore all the possible kernel sizes. So you see that 2, 3, 4, right? 5, 6. So there's a combination of that, the first row, then the second, then the third and fourth and fifth, right? So I try to extract the feature across the length of the time series data. Then, of course, I do the concatenation of this and the features. And then I do the batch normalization, which has been added. And then, of course, ReLU function has been applied. And now I again do the same thing. So I have two blocks here. And once I get the result, I apply again this same thing, what you see on the right hand side, try to take the combination of different kernel sizes. Then I do the concatenation again, then do the bench normalization, and then of course apply the ReLU function. So this is the omniscale block which we have developed. Of course, people have tried this in many different ways, and then that's where I will show and that why we do better, for example. And also, and one of the idea people tried, for example, is try to take, for example, only prime number blocks and so on. Okay, and that does not work. So then we did some, the dimensional reduction using the global average pooling. And then we developed this fully connected neuronal layer network, which basically helps in the classification. And that's our output. So then we detect, as I mentioned, the malicious sensor using the Cornell filter. So we dynamically apply the Cornell filter in all the sensors from where we are receiving the values. Then we predict first the next sensor value. Then we try to find the difference between the actual prediction, the actual value and the predicted value. And then we perform, of course, other idea is like you can use, for example, Gaussian mixture model as well instead of Cornell filter. But we have observed, and then I'll show in the experiment also, that Cornell filter performs better than, for example, GMM. So in the experimental setup, we consider a training set having two real life data with anomalies. One is instant anomalies, another one is the constant anomaly. And we consider a test set having four anomalies like instant, constant, gradual drift, and bias. So as you can see, the test data has all four. And we evaluate our framework on this real data set, SPMD, which is very popular. So safety pilot model deployment, this is from the roadside network. So CVAD basically will predict the instant and constant anomalies. And then we evaluate the performance using, our traditional performance metrics in machine learning like accuracy, F and score. And then I'll show the comparison with the state-of-the-art methods. So the data set, as I just mentioned, is the safety pilot model deployment data set. And this data set comprises of real record high frequency data collected over 100 milliseconds. And this data set has the data from 2 year period of more than 2,500 vehicles. And that form basically a CV network. Trip duration for each vehicle is 2980 seconds. And total 5% anomalies are simulated, and that data is given in this paper. So the sensors which we have considered for our work, one is the sensor S1, which is the measuring the speed, which is the accelerometer, for example. S2 is the GPS, and then S3 basically measures the in-vehicle acceleration. So you can see in the experimental results. So I have the result here for anomaly detection, and which is the incident anomaly, first one with sensor 1, 2, and 3. And you can see the accuracy, precision, and F1 score. So they are pretty good, right, with instant anomalies. Then we have the constant anomalies, again for sensor 1, 2, and 3. And again, you see the accuracy, which is also very good, and also good F1 scores. So on the right-hand side, you can see the confusion matrix for incident anomaly, for example, here. And then the bottom one is for the constant anomalies. Of course, you can see here, that if you have more labeled data, you basically have much better prediction. For example, in the constant anomalies, right, you see that this number is higher, but this number is lower. But of course, overall, you see that we do pretty good, right, with respect to sensor 1, sensor 2, sensor 3. But you see that these values are higher than, for example, the values here with respect to the instant anomalies. Okay? And this is the ground truth, for example, and this is the predicted. So we compare with other methods using the SPMD dataset. So as you can see here that I have this sensor 1, this is sensor 2, and the sensor 3. And the blue basic bar is basically our model. And the CNN-KF is the second model. And there is another paper which uses LSTM kind of with CNN, which is this third. So you can see that we do much better in accuracy. You see 0.99 versus 0.91 with these two other methods. Okay. And the reason, as I said, like, for example, the CNN-KF, right? We are also doing that. But what they do is they basically use this in sequence. So what it means, sequence, like they will apply for CNN, detect the anomalies, and then pass it to Kalman filter. So what basically the problem is, if CNN is using, this detection, and if there are false positives, right? Because if those false positives are there, then those false positives are taken in KF, right? As anomalies. And that's why the sequential method has the problem. And that's why we do, you see those two blocks were in parallel, right? So here is 0.99 for the accuracy. Here's the F1 score, which is 0.83. And if you see the comparison with these two other methods, we do much better. Same thing again with sensor 2. Here actually we do even much better, 0.99, 0.88 with 0.73, which is F1 score and the accuracy. Again with sensor 3, which is again 0.99. So we do much better in terms of the accuracy comparison with these two other state-of-the-art methods. So here is for the constant anomaly. Again, you see that we do 0.98, 0.95, 0.96 in the other two methods. Again, for sensor 1, sensor 2, sensor 3. So you can see that constantly, basically, we are doing much better, right, in terms of the accuracy. Again, you can see here CAVAD 0.98, 0.89, 0.91, right? So we basically perform much better these two methods. Now here is the results for detecting the malicious sensors using the Kalman filter. So if you see with respect to the sensor 1, so this orange line and actually the blue line coincides. And when you see here this red dot, that basically is the sensor which has sent the malicious value at this point. So you can see that it detects, right, the red dot which is the malicious sensor. So at this point, the sensor is sending the malicious value. Same thing if you see in the second one, which is sensor 2. So again, the column filter, you see that this is the prediction by the method, but at this point you see that red dot basically, so the column filter is catching that this is the sensor which is sending the malicious value, and same thing here. So sensor 3, of course, again you see here that column filter is getting those red dots and basically telling that these four sensors or four values are coming from this particular sensor. So we also compared, as I mentioned, with Gaussian mixture model, and that Gaussian mixture model fails to detect the attack sensors. So if you see here, there are two clustered here. One is the yellow and one is the purple, but these red dots are basically the what you call anomalies. So these red dots here and here, they are real anomalies, but you see that even you see that on the prediction, it is saying that this is anomalous, but it is not. So you see that even in second sensor, you see there are a lot of anomalous data. It is saying in the cluster, but they're not actually anomalous. So GMM model does not work well with respect to, in comparison to the Kalman filter. Of course, it detects some, right? But you see that there are several false positives. And of course, same thing with sensor 3. So we have also compared the performance impact of having this amplification block. So you can see that blue bar is basically with amplification block and without the amplification block. Remember that we basically increase the amplitude of the data. So here you can see 0.99, 0.98, 0.83, 0.74, sorry, 0.47. So you can see the accuracy versus the FN score, and having the amplification block basically helps. So same thing, you can see first, this one is basically for the instant anomalies, and then this bottom one is for the constant anomalies. Okay, so basically it shows that having an amplification block helps, okay, in detecting these anomalies. So the idea about this work to develop this robust framework so that we can detect anomalies from the sensor data, and we also detect the sensors, not just the data, and with a very high accuracy and overall like 90% with FN score of 96%. In future, we'd like to consider more types of anomalies and also detect the anomaly type and maybe consider more complex vehicle environments. And these are some of the references which we have used. This is a picture of my group, people who are working on many different projects. And this particular work is actually of the person on the right-hand side. Okay. This person, Sajid. So these are some of the papers on cybersecurity in transportation system from my lab. So you can see that the first one is what I presented. We had papers last year in norms, before that in MDM and ITSC, in 2022, March 2022, 2020, and again in the MDM 2020. These are some of the papers. We have some papers under submission now in the same topic. So I think I'll stop here. If you have questions, please ask.
Thank you, Dr. Madria, for your presentation. I think while we wait for questions, I'll keep an eye on the chat box. I think I can get the ball rolling. So can you comment more on how the factor beta is selected? Because I assume that for different sensors, the
Yeah,
degree to which
right. It will be different depending on the application, it depending on like what types of values you're getting, right? So you have to do some experiments and then, try to detect that alpha and beta both.
and the other question is, so direct amplification is triggered when there is a sudden deviation from a sensor's normal value. Is that, did I understand you correctly?
No, so the amplification is, so for example, if I'm getting the value like 43.0004, right? And 43.003. If you apply all the machine learning algorithm, they'll say there's no difference. Okay. So they will not detect as anomaly. So when we were doing right experiments with the real data sets, that's what we found that no anomalies, but there are anomalies because there are things which are very sensitive to these values. So we have basically changed, right, the amplitude of the data.
Okay, that's good. So I think more to that point though, how do you determine the difference by which you can actually classify as an anomaly? Because for different sensors that'd be different, as you had mentioned, right?
Yeah,
Do you
yeah.
use some sort of
So,
statistics or
right, right. So you have to do some initial experiments, right? And then you basically see that what would be your alpha and beta, right?
okay.
Tho-
And
So that when we are using this CNN model, right? And that basically is trying to detect.
thank you. And the last question that I have is this is more of an open-ended question. So as you had mentioned, there are various sensors in these connected vehicles, right? They perform different intra and inter-vehicle functions. So how do you determine the most critical sensors? I know you had used three sensors for this work, but are there any other sensors that you think, rather than looking at the data from a whole, like doing
Yeah,
sensor fusion, just
right.
knowing the subset of
So,
sensors?
right. So, when somebody is trying to launch an attack, the objective is like, for example, the sensor we have considered accelerometer, right? So suddenly somebody can take control and increase the speed, right? And then there will be a crash. Now, of course, there are other sensors, like in CAN network, right? And those basically packets are unencrypted, right? So they are not encrypted because of latency. So we have paper actually, let me see if I can, you see here, CAN safe,
Yep. Hmm.
a base approach for providing resilience against DOS attacks within the vehicular network, right? So this is very important because in CAN network, this is like, the control messages like when to put the brake, not to put the brake, and those kind of stuff, right? So these packets are unencrypted because, you cannot have latency there. So that basically means this is the attack surface where person can take control on these messages and change the messages. So if you search, you will find more papers coming out in this area. And many people are working because, if things are not encrypted, then this is like open for attacks. So as you can see, this appeared in the ITS conference in 2022.
And I assume MTD is moving target defense,
Yeah,
which
right.
is
Well,
yeah,
different.
that's a
So that's
novel.
the approach we try to apply here in
Got it.
our, you know,
Got
which is kind of very novel, We try to use MTD here, because the idea is to confuse, right?
it. Right.
The
Mm,
attacker.
got it. Well, I think I'll wait for a few more questions. Looks like there aren't any more questions. Dr. Madria, thank you for your talk. You'll receive a nice plaque from us, from the University of North Dakota, and also a certificate signed by our dean, recognizing your initiative for delivering this, being part of this webinar. So thank you again, and we look forward to working with you in the future as opportunities arise. Yeah.
Thanks. Thanks a lot. Thank you.